My name is David Cole. I am a graduate student at the University of Wisconsin. I work under Dr. Victor Zavala there, and we've been using graph-based approaches, particularly in Plasmo, to represent optimization problems. So in our research group, we often think about how we abstract or represent the problems we're looking at, and we found that graphs are a powerful way of representing a lot of optimization problems. You can see here how dynamic, stochastic, PDE, and network optimization all can be represented within the graph structure. And in Julia, this can be done through a package called Plasmo, and I'll give just a brief overview of the package here. It was developed by Dr. Jordan Jalving, who's also an alum of our research group. It's built on this abstraction called an optograph. Mathematically, that's represented in the top right here, where you have local constraints on your nodes and linking constraints on your edges. So your nodes can contain objectives, variables, and constraints, and then edges contain linking constraints for variables that are on two or more nodes. So this is technically a hypergraph because you can have an edge that connects more than two nodes. Plasmo also extends JuMP, so a lot of the JuMP functionality is also applied here. You can instantiate a graph with this optograph function, and then you instantiate nodes on that graph, and then the at constraint and at variable and at objective macros are all extended, so you can add those directly to the nodes of the graph. You can also add linking constraints through the at link constraint macro, and that's what creates your edges in this graph. One of the other useful things about Plasmo is it supports hierarchical or modular model buildings. This is actually similar to the blocks that Bethany just talked about earlier, in that you can build a single graph, shown here by this blue G11, and then you can add that graph to a higher level optograph, represented by this red box. And each of these subgraphs can then be optimized independently, and that will be useful for some of the decomposition schemes I'll talk about. And there's really not a limit to how many nested subproblems you can have within a graph. And so you can create these hierarchical or multi-scale structures fairly readily within Plasmo. As I mentioned, we just released last night Plasmo version 0.6, so this had some exciting changes. For one, it's more subgraph-centric, so previously each node was a JuMP model. Now each subgraph is a JuMP model, which is in the back end. This is a little more efficient on the memory usage. We also finally updated to the new JuMP functionality, so all the at and L macros are gone. I know this was like a year ago that this happened, but as of last night, you can now support nonlinear constraints with that constraint. This also means formerly edges were link constraint refs. They were a special type. They had to be linear. Now they can now support nonlinear on the link constraints. So we're excited about some of these changes. So for the rest of the talk, I'll be talking about how we use these graphs for decomposing optimization problems. So Bender's decomposition, shown here, is one of the approaches that, well, the main approach I'll be talking about today that we've been implementing. So in Bender's, you break your problem into a master problem and a subproblem, and you solve these two problems iteratively, passing primal and typically dual information between the two. We can think of this though as being in a graph structure. So if we have the graph shown here on the right, where these nodes could be, for example, a subgraph, we can treat these two nodes as a master problem and a subproblem and apply this Bender's decomposition to this. For those not familiar, Bender's decomposition looks like this. So for this graph in the upper right, where we have two nodes, these nodes could be subgraphs. Just use nodes here for simplicity. Each of these subgraphs could embed this optimization problem on it and have this linking constraint C1 between those two optimization problems. So this full graph would be the optimization problem we want to solve. But we can set one of those nodes as the master problem and one as the subproblem. And in Bender's decomposition, you add this theta variable to the master that is a lower bound on your subproblem. And that theta is constrained to be greater than or equal to a set of cuts that come from solving the subproblem. And then on the subproblem, we enforce the constraint C1, which is your linking constraint, and we fix the solution of the master variables in that subproblem. And since theta is a lower bound on the subproblem, when you solve this master problem, you get a valid lower bound on the overall graph. And then when you solve these two problems in sequence, since we're fixing the primal solutions of the master problem, we get a valid feasible solution that creates an upper bound on the problem. And so in Benders, you iteratively solve these two problems and you pass dual information back to create cuts. And as you do this, your upper bounds and lower bounds will hopefully converge to your optimal solution. You can also expand this approach to include something called nested benders or dual dynamic programming. And in this case, you have a series of these subproblems, and you actually solve each subproblem in a forward pass, passing primal information each time, and then you do a backward pass where you share the dual information, or you share feedback to create the cuts. So what I've been working on as part of my PhD has been developing a package. It's currently called Plasmo Decompositions. This is a working name. It's not released yet. This might change a little bit when we release, which we're hoping to do in the next month or so. But you create a graph structure, and then you pass that graph to this Plasmo Decompositions package, and it will make the changes to the structure that you need to apply these decomposition schemes. So it will also test to make sure that you have the correct structure. So for example, nested benders decomposition, you need a tree structure. And then once you've defined that structure, you pass, for example, the structure on the right, and it will make those changes, adding your cost-go variables and enforcing your linking constraints on the subproblem. One thing I want to note here is also that the graphs, one of the powerful things about the graphs is that they're agnostic to any sort of domain. So once you've built this problem and you pass it to Plasmo Decompositions, it doesn't care whether you're going across time or space. It just goes off of the graph structure. So actually in this top right example, we could set either problem as the master problem and apply Bender's decomposition. One will very likely be more efficient than the other. So this gives the user a lot of flexibility in how they're defining and decomposing the problem. As an example of this, this is just a small proof of concept example. This is actually implemented in GenX. In this paper that I'm citing here on the bottom, Filippo Pecci and Jesse Jenkins introduced a regularized Bender's decomposition. And they use GenX. GenX is a capacity expansion modeling package where you have a lot of flexibility in defining data and constructing your problem. And so I worked with Filippo in building this problem in Plasmo. And in this case, we had one node or subgraph that represented the planning master problem, and then there are these n operational subproblems that weren't linked together. They were only linked to the master graph. And you can see in the top right what it looks like to call Plasmo Decompositions, that we pass our overall graph G. We set a master node, which is the master graph object, and then there are several options that we can pass to this optimizer object, including using regularization, using multi-cuts, adding slacks. This ensures your subproblem is feasible, or parallelizing benders. So in this case, we can parallelize the solve of each of these subproblems. And then in the right here, on the bottom right, you can see the behavior of these upper and lower bounds, how after takes several iterations converge. Here we needed 32 iterations before both those upper and lower bounds converged. And this is a pretty small problem as far as LPs go. This is only 120,000 variables. With the decomposition approach, this took about as long solving with decomposition in highs as solving the full problem without decomposition in highs. If anything, I was a little surprised it took the same amount of time. I expected decomposition for a problem this small wouldn't actually, I expected it would be slower. Decomposition approaches typically are most useful when the problems get very, very large. One last example I'll share just briefly here, I want to give some time for questions, is something that I did as part of an internship this last year. I was at the National Renewable Energy Lab working with Omar Guerra on problems with long duration energy storage. We were solving a production cost model, and one of the challenges when you add long duration energy storage to these is that you need longer time horizons to capture the value of that storage today. So Jose yesterday gave a great talk on Sienna. We were using Sienna, and I mapped the power simulations JuMP model into Plasmo to apply Plasmo decompositions. So I'll just share one quick example. This is from a fairly simple 5-bus system. You can see the system structure in the top right and the graph representation here in the top left. This is for a single day. So we represented each bus and each line with a node. And you can see that originally the structure is not a tree, but you can partition and aggregate sections of your graph to create the tree structure you need. In the bottom right, you can see the results for this. NBD is nested Bender's decomposition. The subproblems are solved with Gurobi, and then we solved the full problem without decomposition with Gurobi. And we actually were able to get pretty good results here. We got to, in under an hour, we got to a 0.2% gap. We solved this for a full year, 52 weeks, with 2 weeks as the subproblems. And we actually solved faster than Gurobi. In this case, this is largely that Gurobi would get to a really good solution, but it had a hard time closing the gap. And after talking to Jose yesterday, I think part of this is that there's a lot of equally good solutions, and Gurobi has a hard time picking of completely closing that gap when there's so many roughly equally optimal solutions. We did try this on a larger problem. In this case, I'll just point out our time here in the bottom right was not as good as solving the overall problem. This is for a 31-day horizon on a larger problem. However, there is a substantial memory saving from the decomposition approach, which can help facilitate using smaller machines or non-commercial solvers as well. With that, I just want to recognize some of our collaborators. I really appreciate Jordan has put in a lot of work on Plasmo and maintaining and supporting it. I also want to recognize Dr. Gangamanavar and Omar Guerra, who were collaborators on this work, and recognize the NSF for their funding of this. And with that, I'm happy to take any questions.